Right after today is done, we are actually halfway through the semester. Today's the 20th day of class. There's 40 days of class total. It's lecture 18 because we had 2 test days. We'll have 36 lectures total, I guess, although Friday, the 26th of April, I'll be gone to California, so we won't have class that day. So I guess we'll only have 35 lectures. We have Good Friday this week. Next Monday is off as well. So 2 days this week, 2 days next week, 2 days the week after that too, because April 10th, Wednesday, is advising day. So lots of breaks. It can be easy to get distracted, but you want to keep on task. Trying to finish up chapter 12 this week. And next week go into chapter 13, which means next week we get into integration. Double integrals, triple integrals, applications, applying polar coordinates to double integrals, and something called spherical coordinates to triple integrals. And then we do line integrals, vector fields, surface integrals, some important theorems, Green's theorem, Stokes theorem, that ends up the semester. And that's the hardest part, is those things. They're not too bad to do, fairly simple examples, but what's harder is just understanding what it all means. That's the hardest part, is just conceptually. Before we do our main topic today, which is optimization, I would like to linger a little bit more on the chain rule, in particular in using it with polar coordinates. Let me remind you, first of all, what we did last time. So no official homework assigned directly related to polar coordinates yet. But I think it's good to introduce it now because it's relevant for the thinking about the chain rule in important situations. X equals R cos theta, Y equals R sine theta. The picture for this, a generic picture, if your point is in the first quadrant, is that, this number here is X, this number here is Y. So if you've got a right triangle like this, where this distance is X and this is Y, the hypotenuse has length R, and the angle theta is the angle with the positive x-axis. And you can derive these two formulas using SOHCAHTOA. Sine of theta is Y over R because that's opposite over hypotenuse. And cosine of theta, adjacent over hypotenuse, is X over R. And that helps you come up with these. But also from the Pythagorean theorem, R is the square root of X squared plus Y squared. And theta, well, this is a little funny. It's, if you want to be extra precise about it, it's arctangent or inverse tangent of Y over X if X is positive, so that you're in the first or fourth quadrant, because arctangent always gives you an answer back between negative pi over 2 and positive pi over 2 radians. It's actually arctangent of Y over X plus or minus pi. Let's see. If you get an arctangent, if your angle is actually over here, then you can just do plus pi in both cases. You could also do minus pi. Plus pi if X is negative. And if X is 0, it's either pi over 2 or negative pi over 2. If X is 0, it depends on whether Y is positive. This is if Y is positive, and this is if Y is negative. So effectively, up to angular multiples of 2 pi being added to this, effectively, this is the formula you can use. Though most commonly in terms of derivations, we use the simplest form of it right there. I showed you last time that you could take a function z of 2 variables and replace x and y with r cos theta and r sine theta, and use the chain rule to ultimately find dz dr and dz d theta. That's what we focused on last time, but you actually can do it the other way around too. Maybe you've got a function best described in polar coordinates first. And you want to figure out its dependence on rectangular coordinates. Maybe you've got z equals f of r theta. It's just simplest to describe your function in polar coordinates at first. But then you want to figure out how it depends on x and y. Yeah, effectively you can replace r with square root of x squared plus y squared and replace theta with arctangent of y over x. Or maybe this more general kind of crazy thing here. It gets a little confusing. But just to keep it simple, pretend that works. Pretend x is positive. And get a function that depends on x and y. And you could try to figure out the partials of z with respect to x and y in terms of the partials of z with respect to r and theta first. You can use the chain rule effectively in the opposite order. The diagram in that case would look like this. You'd think of z as depending on r and theta first, and then r and theta depending on x and y. So you take the partial of z with respect to r, multiply it by the partial of r with respect to x, add the partial of z with respect to theta, and multiply that times the partial of theta with respect to x. And then with respect to y, you could do something similar, except replace the x's with y's. In both spots. And just like you could simplify that these derivatives using these equations last week, so you can technically simplify these things using these equations. Again, for simplicity, assuming it's the arctangent of y over x one. I mean, the derivative of this one's going to be the same because adding pi doesn't have a different derivative. So for example, r being the square root of x squared plus y squared, which is x squared plus y squared to the 1/2, means the partial of r with respect to x from the chain rule is 1/2 x squared plus y squared to the negative 1/2 times 2x, which is x over the square root of x squared plus y squared, which should look familiar from the exam. And that, while it's true that's the derivative of r with respect to x, could also, using the fact that the square root is r, be written as x over r, which is kind of convenient. The partial of r with respect to y is something similar, except you get y over r in the end. Kind of convenient. How about the partial of theta with respect to x and y? Oh, I got to take the derivative of arctangent, I guess. Derivative with respect to y looks a little easier. Well, let's do it with respect to x first. I need the chain rule. Derivative of arctangent is 1 over 1 plus whatever's inside there squared. But then from the chain rule, I need to multiply that times the derivative of y over x with respect to x. Use the quotient rule. Low d high minus high d low, differentiating with respect to x over the square of what's below. I'm not assuming y is a function of x, so its derivative with respect to x is 0. This simplifies to negative y over x squared. Bring the negative y up top, multiply the x squared through the bottom here, it'll become x squared plus y squared. Do you see that? You multiply that x squared down there, it'll cancel with the x squared here. You have an x squared there. It'll simplify to that. And this is negative y over r squared. Kind of cool. How about the partial with respect to y? It's going to start the same, but then the derivative of y over x with respect to y is just 1 over x. Right? Differentiate with respect to y. Y is to the first power. 1 over x is a constant. You get that constant. Let's also, for the sake of multiplying through the bottom by x squared, multiply the top and the bottom of this by x, which doesn't change it because it multiplies it by 1. And it's going to simplify to x over x squared plus y squared. X over r squared. These formulas that I'm deriving are useful. And they also can help you derive strange looking things that are sometimes useful, like what I'm about to show you here. Like this equation, which gives you the squared magnitude of the gradient vector in polar coordinates. Where does that come from? Effectively just uses the equations I just found. U, what is U? U is just a dependent variable name that I'm using here instead of Z in this formula I've highlighted. Might be better to use the function name f instead of U, but it's somewhat traditional to use the variable name. U is actually a common dependent variable name in this context, especially when you're talking about partial differential equations. U is commonly used with partial differential equations. Could represent a temperature distribution. Could represent, like for a wave, could represent the magnitude of the wave or the displacement. This is useful for, you ever heard of Laplace's equation and the wave equation and things like that? That's where this kind of notation comes into play. We're interested in the gradient of U, which you could also write the gradient of F. It would be this vector. I could write both of those derivatives like this. And I could replace the partial of r and theta with respect to x and y with these things that I derived. I'm using U instead of Z, but this is what I'd be using. Let's go ahead and rewrite it. So I'd get partial U partial r times partial r partial x plus partial U partial theta times d theta dx. Do the same thing with y instead of x. Looks pretty similar. It can be easy to get confused here and write something wrong. So I'm trying to be careful. And then again, you could replace these derivatives with the formulas that I just derived 5 minutes ago. Partial of r with respect to x is the same as x over r. So I could write x over r times the partial of U with respect to r. I'll just write that as U sub r. Partial of theta with respect to x, that was the negative y over r squared times the partial of U with respect to theta. I'll just write that. So this is going there and this is going there. Do the same kind of thing over here. Partial of r with respect to y is y over r times ur. The ur comes from that. Partial of theta with respect to y, that was the x over r. X over r squared times u theta. And then I could try to find the magnitude of this vector and square it. Does everything work out nicely? I didn't try this ahead of time, so I'm not sure how well this goes. Taking the magnitude squared avoids square roots. So I got to square this thing. and add the square of this thing. I'm doing a dot product effectively of this vector with itself. Is this going to simplify nicely? It's not so clear. We might get some cancellation from outside and inside products here between the two terms. If I square this, I get x squared over r squared, ur squared minus, okay, the outside and inside products is going to give 2xy over r cubed, ur u theta. Last times last will be y squared over r to the fourth, u theta squared. I'm squaring just this thing so far. Square this thing, y squared over r squared, ur squared, plus 2xy over r cubed, ur u theta. These are going to cancel. That's awesome. And then plus square this last one, x squared over r to the fourth, u theta squared. Then combine, looks like I should probably combine these and factor out common factors. So it looks like I get x squared plus y squared over r squared, ur squared, plus x squared plus y squared over r to the fourth, u theta squared. And lo and behold, that's r squared. And this is r squared. So we get more cancellation. Completely cancel and partially cancel. ur squared plus 1 over r squared u theta squared. The ur and the u theta are derivatives, rates of change. The r itself is not a derivative. It's a polar coordinate. This kind of thing, weird as it seems, has got plenty of applications. You'll see if you take classes like maybe mechanics or maybe electromagnetism and that kind of thing. You'll see polar coordinates used a lot. It can be visualized. I'm doing it for a particular function here, x squared minus 2y squared. I'm trying to understand intuitively the meaning of this. What did this represent again? It represented the squared magnitude of the gradient vector. That's what it represents. Take its square root to find the magnitude of the gradient vector itself. And so what I'm trying to show here, I know it's kind of small. These are the level curves of the function. Notice I've got the circle that's the radial at the radial coordinate of the point, and I've got the ray that's at the angular coordinate of the point. The graphs over here and here are the effectively taking the function of two variables and restricting it to the circle and the ray and seeing what the graphs look like. Notice theta is going from 0 to 2 pi. So I'm going around the circle, and r, the radial coordinate, is going from 0 out technically to infinity. And I'm seeing the behavior of the function. I did plot the gradient vector here, though it's kind of hard to see. It's this black arrow at this point. It is, you don't see the level curve at that point. I could move it to try to put it on a level curve more precisely. The gradient vector is perpendicular to this level curve here. It's pointing from dark to light at that point. We're interested in understanding the size of the gradient vector. And effectively, especially if we're at a radius r that's far away from the origin, r is large, what you can think of intuitively is that if r is large, this quantity is probably a lot smaller than this quantity. So the size of the gradient vector is more affected by the derivative in the radial direction along the blue line, the rate of change in the blue line, than it is by the derivative in the angular direction, theta. I don't know that that's so intuitive there. I mean, the slopes of these graphs, you could try to eyeball them. This slope looks like it might be in the ballpark of -20 or something, and this one more like -10. But evidently, it's this derivative, its magnitude, that affects this more. You'd have to move the point around and try different examples to see that more clearly. But that is a step toward trying to understand the meaning of this equation. And this equation, and guarantee you would come up in an advanced physics class. Okay. This is showing you the process, the problem-solving process for doing this kind of thing. Polar coordinates is useful for more than just doing double integrals, as we're going to use it later in the course. Plugging in points would give you numerical values too. You can certainly plug in points to find numerical values of these of the derivatives here. All right, our main topic today is optimization. Using derivatives, just like in Calc 1, to find critical points, classifying them as maxes or mins, or maybe neither. Start with a couple examples where you don't have to use derivatives, but you can just think about it. And actually, this first example is at least somewhat similar to the example I did at the beginning of chapter 12. Take f of xy to be the square root of, say, something like 1 minus x squared over 9 minus y squared over 25 or something. Some example somewhat similar to this was our first example in chapter 12, when we were thinking about functions of more than one variable. I'm interested in optimizing this function, finding its maximum and minimum values. We have to be a bit more careful about domains. When you say find maximum values, what domain are you talking about? If it's not specified, it's the maximum possible domain, the biggest possible subset of the plane on which this function is defined, getting you real outputs. If we allowed for imaginary number outputs, then what's under the square root could be negative, but we're not doing that in this course. So for the domain, we require 1 minus x squared over 9 minus y squared over 25 to be greater than or equal to 0 for the domain. So in other words, this inequality defines the domain. I.e., the domain, you could call it D, is the set of all points in rectangular coordinates satisfying that condition, which could be rewritten as the set of all points satisfying this inequality, x squared over 9 plus y squared over 25 is less than or equal to 1. This is called set builder notation. You read this as the collection or set of all points x, y in the plane, which you could call R2 if you like, satisfying that inequality. Alternatively, that's the set of all points in the plane R2. This funny looking E means in, satisfying this inequality. And if you graph the corresponding equation there, it's an ellipse with x-intercepts at -3 and +3, and y-intercepts at -5 and +5. If you imagine setting this equal to 1 and think about finding x and y-intercepts, if for x-intercepts you'd set y equal to 0 and solve for x, and you get x squared over 9 equals 1. So x is plus or minus 3. And for y-intercepts, you'd set x equal to 0. Solve y squared over 25 equals 1. You get y equals plus or minus 5. And that ellipse is the boundary of the domain. The ellipse is boundary of D. There's a somewhat common notation for the boundary of D that makes it look like a partial derivative of D. So there I'm using the del curvy D symbol, whatever you want to call it, partial derivative symbol, as if I'm taking a partial derivative, but I'm not actually. It's just a special symbol for the boundary of D. There's actually a little bit more meaning behind this than what I'm indicating. but effectively this is good enough for what we're doing here. That ellipse, and then the interior of the ellipse is also including in D itself. So D itself is the inside of the ellipse, the interior, and the ellipse itself. This is the union of the inside of the ellipse unioned with the ellipse itself, which is this boundary of D. This is the union symbol. It just means combine the sets. This is an example of something called a closed set. Remember closed intervals? Closed interval is an interval written like that. On a number line, it's all the numbers between A and B, including the endpoints. You might think of the endpoints as being the boundary of the interval. Maybe we could even write the boundary of this is the two-element set AB. And we call it closed because it contains those endpoints. If it did not contain the endpoints, we'd call it open, an open interval. It's kind of like the boundary, those endpoints kind of close off the interval. Nothing past them is in it. If we did not include the boundary, the boundary points at A and B, that's an open interval. And, open intervals are a little funny if you think about it. That interval there doesn't have a highest point or a lowest point in it. A is not the lowest point because it's not in the interval. B is not the highest point because it's not in the interval. These subtle points I'm making are really important. As an example, the open interval from 0 to 1 doesn't contain 0 or doesn't contain 1. There's no biggest number in this interval. There's no smallest number in the interval. 0 is not the smallest number because 0 is not in the interval. 0.1 is not the smallest number because you can go less than 0.1. 0.01 is not in the interval, not the smallest number because you can go less than 0.01. Is dx the smallest number in this interval? We're not going to go there. No infinitesimals right here. Okay, this is real math, not hyper-real math at the moment. Real numbers, not hyper-real numbers. Coming back here, this set D, this domain, is a closed set. It contains its boundary. Closed set contains all its boundary points. Points along the edge. What is the technical definition of a boundary point? What I'm talking about here is that near the beginning of chapter 12, actually. We are going to have some problems near the beginning of chapter 12 again, though our main problems are near the end. This is the section about limits, this terminology. What does it really mean to be on the boundary? It means if you take an open disk near the point, no matter how small, there's points both in the set and outside the set, inside that disk. Say it again. This point that I drew here, this dot, is on the boundary of the red set. Intuitively, the boundary there, that's the ellipse, is like a fence separating the set from the outside of the set. Technically speaking, that means no matter what disk I put around that point, no matter how small, there's points inside the set and outside the set that are in that little disk, no matter how small the little disk is. Those are the boundary points. And the set overall is closed because it contains its boundary points. On the other hand, a set inside the boundary is in the interior of the set. It's not a boundary point, which means there's at least one disk, in fact, infinitely many, if they're small enough, around that point that's completely inside the set. Are there open sets as well as closed sets? Uh-huh. If we got rid of the boundary, the resulting set would be an open set, and every point would be an interior point. This has relevance. And what I'm talking about here is not completely irrelevant to optimization. I got to go quick here. You can optimize this function without calculus. How? Think about it. Yeah, just think about it. Thinking about this function over this domain, as you approach the boundary, what happens to it? The outputs get close to square root of 1 minus 1, because you're getting close to where this equals 1. The boundary, the ellipse. And in fact, along the boundary, along this ellipse, it equals 0. The output of the function is 0. So this function has a minimum value of 0 along the boundary. F has a minimum value of 0 along the boundary of D at all points along the boundary. In fact, you could say it's an absolute minimum, as the book does. I prefer the word global. I'm going to put both words there, global / absolute minimum value. It's as small as it can be, globally, absolutely. It's got a maximum value. Where's the biggest this could possibly be? Is square root of 1 is the maximum value, because if you're at the origin, if x and y are both 0, that makes this what you're subtracting as small as possible. You're subtracting 0. So the resulting thing, 1 minus that, is as big as possible. Square root is also as big as possible. F has a global / absolute maximum value of square root of 1, which is 1, at one point, x, y equals 0, 0. That it's got a global max and min value is guaranteed by a very important theorem called the Extreme Value Theorem. I'm not going to write it out, but I want to emphasize that that guarantees F has a global max and min value over D. What does it say? It says if you've got a continuous function, if F is a nice continuous function, and the domain happens to be closed, meaning it's a set containing its boundary, and bounded, meaning it doesn't go off to infinity in some direction. By the way, you can have closed sets that do go off to infinity that are unbounded. For example, the entire upper half plane above the x-axis, including the x-axis. It includes its boundary, which is the x-axis, but it goes up forever and ever. It's unbounded. There's a distinction there between boundary and bounded. You want to make sure you understand the distinction. Boundary in that case is the x-axis. It's the edge, the fence of the domain. But it's not bounded because it goes up there forever. It's everything above the x-axis. This is a bounded set. It doesn't go off to infinity, off forever and ever in some direction. It's a bounded set. When you have a continuous function on a closed and bounded set, it's guaranteed to have a maximum and minimum value. In fact, global max and min. Ultimately, for your homework, though, you're mostly trying to find what are called local maxes and mins. This function also has a local max and min where it has global maxes and min. Global implies local. The book uses the word relative instead of local. I prefer the word local. But you'll see absolute and relative in the reading. I use global and local. Global implies local. So these things that are global maxes and mins are also local. But what's most useful, the main thing we want to do is think about using derivatives to find maxes and mins. Oh, I thought I had an example here. Maybe it's in the Mathematica. Let's see. That's not what I wanted to do. Where's the example? I thought I had an example in here. Okay, let's take an example from the book. I thought I had my book. Where is it? Sure, I'll use yours. I thought I had mine with me. I've just forgotten it. We mostly, though, want to learn how to find local maxes and mins with critical points and derivative tests, just like in Calc 1, but now we're generalizing them to Calc 2. Let's consider an example that happens to be one of your homework problems. So we'll do one of your homework problems here. I'm picking the one that looks like it might be the hardest one. It's section 12.8, number 12. The function is z equals f of xy is x to the fourth minus 2x squared plus y cubed minus 27y minus 15. I want to find local extreme points, relative extreme points of this, with the same process as Calc 1, except generalized. In Calc 1, you took the derivative, set it equal to 0, solve for x to find the critical points. Then you test, do those critical points give you a max or min or neither? There's a first derivative test and a second derivative test. Here we do the same thing, except we take partial derivatives. We set them both equal to 0, solve the resulting system of equations, and we only use a second derivative test, not a first derivative test. We look at the sign of the second derivative effectively, not quite, but almost. Instead of thinking about whether the first derivative changes sign from positive to negative or something like that. I don't know if you remember that from Calc 1. Might have made number lines and marked off where it's positive and where it's negative, that kind of thing. All right, so what are the partial derivatives here? dz dx, or fx if you prefer, be 4x cubed minus 4x, which you should probably factor. It's almost always a good idea to factor things as much as possible, because you're going to be setting these things equal to 0 and solving for x and y. Partially, what makes this a little easier than it might be in general is that these derivatives are in the end functions of one variable, so that makes it a little nicer. Once again, factor as much as possible. Sometimes you might have to use the quadratic formula, but in this case, we can factor. Set these both equal to 0 and solve the resulting system of equations. As I just said a minute ago, in general, it's possible both equations could involve both x and y. It could be a nonlinear system of equations to solve for x and y that could be pretty challenging to solve. But in this case, it's not too bad. You see that here, x is 0 or 1 or negative 1. And here, y is 3 or negative 3. That actually results in 6 critical points. For each combination of those. X is 0, y is 3. X is 1, y is 3. X is negative 1, y is 3. X is 0, y is negative 3. X is 1, y is negative 3. And x is negative 1, y is negative 3. We want to classify these. We want to use a second derivative test to classify it. Do I look at the sign of the second derivative? Sort of. you need to take second derivatives, but there's more than one of them. fxx is 12x squared minus 4. I'm going to put these in a certain pattern here. fxy, let's put that to the right of that. Differentiate this with respect to y, you get 0. fyx, the other mixed partial, it has to be the same thing. 0, and it is. And fyy, differentiate that, you'll get 6y. You don't have to do this, but you can think of this as a matrix. You don't have to do that, but you can. And you can write down something called D, which is the determinant of this matrix. However, it's not typically called a determinant in this context. It's typically called a discriminant. Still starts with D. It is the determinant of this matrix, though. It's fxx times fyy minus fxy times fyx, though because of the fact that fxy and fyx are the same, I can write that as a square of fxy. How does this simplify for this example? It simplifies to just multiply these. 6 times 12 is 72 x squared y minus 24y. For this example, it might be simpler to write that as 24y times 3x squared minus 1. Not that you have to. Then you take this discriminant and you plug in the critical points. It discriminates the types of critical points that you get. If when you plug in a critical point, you get a negative discriminant, that means that critical point is neither a max nor min, but something called a saddle point. That if you looked at the graph, you could sit on it like a saddle. I'm talking about the three-dimensional surface. That's the graph of the function. It's called a saddle point. It's a max in one direction and it's a min in another direction, if D is negative. If D is positive, then the critical point is either a max or a min, but you have to do something else to figure out which. So let's try some of the examples here. What's D evaluated at 0, 3, for example? You plug in critical points here. 0, 3 was the first critical point. You don't plug in other points, just plug in critical points. X is 0, y is 3. If I use the second formula, I get 24 times 3 times negative 1. Negative 72. But the important thing is that it's negative. That means 0, 3 is a saddle point. Next critical point, 1, 3. You get 24 times 3 times 3 minus 1, which is positive. So it's not a saddle point. Is it a max or a min? Plug the point into fxx as well to figure out if it's a max or a min. If you do so, fxx is 12x squared minus 4. You get 12 minus 4 is positive. Effectively, what that ends up meaning is the graph is concave up near the point. It's a min. You might say, well, it's concave up in just the x direction. But it turns out it'll be concave up in the y direction as well. If you had plugged this point into fyy, you also would have gotten a positive number. It's good enough to just plug it into one of them. This means, these two things mean 1, 3 is a local min or relative min. Try the next one. The next one was negative 1, 3. That also gives you a relative min because it also gives you the same value of D and same value of fxx. Why? Because of the squaring involved. Because you got x squared there. Notice that FYY would still be positive because the y coordinate is positive. -1, 3 is also a local min. It's got 3 more points. It's D of 0, -3. Plugging into D here. 24 times -3 times -1 positive. That's something different than happened with 0, +3. If I plug this into fxx or fyy, I get a negative number. That means 0, -3 is a local max. The negative fact there effectively means the graph's concave down near the point. So you get a local max. D plus or -1, -3 maybe are both the same. Yeah, and in both cases you get a negative quantity. Those end up being both saddle points. Are saddle points. I'll let you check that. Let's end class by seeing if we're right by a graph. Contour plot of this function. What's the function? X to the 4th minus 2x squared plus y cubed minus 27y minus 15. The minus 15 doesn't really make much of a difference for the locations of the maxes and mins. Does it seem like we're right? Hard to completely tell. Looks like this, so it's darker up here, so it's close to minimums up there. And in fact, at the 2 eyeballs, so to speak, that's probably where there's a minimum. These two, -1, 3, and +1, 3. And in the middle, at the nose, probably a saddle point, 0, 3. Down here, the maximum, the lightest part, is supposed to be at 0, -3. These are supposed to be saddle points, which seems reasonable since they got kind of curves that are not circular near these points. You'd have to zoom in there to believe it more clearly. Let me say one more thing. Back in the other kind of problem, where I'm thinking about the domain and thinking about it intuitively, if I had thought about this function, 1 divided by that square root for the natural domain, it would be everything inside the ellipse, but not on the ellipse, because if the point was on the ellipse, we'd be dividing by 0. And the resulting domain would not be a closed and bounded set. It would be an open and bounded set. And there's no guarantee of a max or min. And in fact, this function does have a min at the origin, but it has no maximum. It's like it's got vertical asymptotes near the boundary of the ellipse. All the way around the boundary, there's like one big vertical asymptote. And you could graph it to see that. Okay, so the domain does matter, is the final point I wanted to make about that. But I forgot to at first. Okay. See you on Wednesday.